Hello everyone, welcome back to ECE350 again. It's lecture 8, part number 2. So today I'm gonna go into the Smith chart and learn more about it and use it to do some calculation, okay? First of all, Smith chart has, we understand what is inside here. Inside here, there are complete circle. These are the, let me make it bigger. These are the real part of the load, and these are the reactive part or imaginary part of the load. You all know that. Then also there are three circles here. The innermost circle right here, these are in degrees of that R was the reflection coefficient. So if you look at back here, so look at this 30 degree here, 40 degree here. So this is the innermost circle uses for the degrees of reflection coefficient, right? Then there are two other circles here. The outermost circle, if I break the outermost circle over here, this one is the wavelength towards the generator. So if you go this way, over here, you're going towards the generator. What does means? Let me show you here. What does it mean? So you have a load over here, right? This is the load over here. So generator is somewhere here, right? So I'm gonna let me connect it. So this is your generator, right? So if you walk this way towards the generator, that means you're walking in your Smith chart clockwise. All right. So then the second innermost middle circle over here, that represents the wavelength when you walking towards the load. So that means if you walk this way now here, if you now walk this way, that is the middle circle towards the load. So the two walking, one is towards the generator, one is towards the load, right? So that's how you measure how much you worked. Everything in terms of lambda. And as you know from the previous lecture, if I walk the whole circle, if I start from here, let me get a different color. If I start from here and work towards the generator and come back to the same point, I traveled half lambda. All right, we proved it in last slide. Same way, if you go other way around, also you traveled half lambda. So if you travel the whole Smith chart circle once, you travel half lambda, and you come back to the same place. Okay. All right. How do you find reflection coefficient? So let's say that you have a point over here. This is normalized impedance 2 minus 1j. So I have to find that 2 minus 1j. So let's come back here. So this point, this is the real impedance. So there's 2 right here, and 2 minus 1 minus means is negative impedance. So that's negative 1 here. If you look at here, this is the one circle over here. So if I follow it, that's right. So I'm here. So that's my load, right? So I have to take a roller. I need to take a roller over here and measure from here to here, right? And also have to measure the complete circle, which is my distance, which is 1. So if I now try to find the magnitude of the reflection coefficient, I will take the ratio of this measurement and with respect to ratio of this measurement over here, so OP over R, that is 0.45. So that is your reflection coefficient. And reflection coefficient angle, now if I look at this one here, so I extend this one to the all the way out there. So if you look at carefully over here, so innermost one will give you the angle. So at this point over here, whatever angle is negative 20 here, 30 here, so it will be around 26 if you look at the Smith chart. So that is 26.26 negative, because we're going clockwise from the zero angle here. Okay, so that's how you find the reflection coefficient. Again, if you walk through the line, let's say you have a let me draw it over here. Let's say this is your ZL, and if you walk this way, distance D, so your impedance become ZD. That is also can be expressed in your with the reflection coefficient at that point. So what is gamma D? You have seen that before. That is a gamma D here, right? So how much you walk? D is in terms of lambda. All right. So that will give you the reflection coefficient at any point, again, it does not change the magnitude, only change the angle. All right, so now let's do a quick example here. I'm trying to find ZD, which is the impedance at any point of the line. So what it's saying over here, I have a load over here, right? That load is 100 minus J50 ohm, right? Then D, so I'm trying to find my impedance at this point over here. What is D is 0. Again, as I said, this in terms of wavelength, lambda. What would be the ZD over here, right? So to do that, first thing first, I have to find the, what do you call it, normalized value of this, and find it and put it on the Smith chart. So let's find the normalized value of that. So normalized value of that would be, let me see, normalized value of that would be, if I do it over here, my Z0 is 50, should be, so normal, let me find the normalized value over here, would be 100 minus J50 over 50, so that will give you 2 minus J, right? 2 minus J. So let's put the 2 minus J. So if I look at here, 2 minus J is that point over here, right? So 2 minus J is that point. So I'm gonna extend it to the all the way out there and find the point right here, right? That point is 0.278 lambda. If you look at here, 0.28, 0.39, so that point is 0.287 lambda. So that is my current point of the load. So that is my distance right here. That is my point right here. This point over here is 0.287 lambda, right? So I have to go 0.1 lambda towards the generator. So remember that if you go clockwise, you go towards the generator. So I'm gonna go from here 0.1. So 0.1, if I add 0.1 to this one here, I'm gonna get 0.387 lambda, right? So this right here. So I'm gonna find the point at 0.387 lambda. Then I'm gonna draw a line from that point to the center. That line right here, green one. Then also from that, from this point, I'm gonna draw a circle with this radius from the center here, because that radius will give me the same reflection coefficient magnitude everywhere. Your angle could be different, but diffraction coefficient everywhere is the same, right? So that's why this point over here, point B, will give me, at this point will give me normalized value of ZD right here. So this point will give me normalized value of ZD, because if you look at, come over here, let me show you, your ZD over here, right? It depends on where you are with your gamma D. So gamma D does not change, your gamma D does not change the magnitude, only the angle. So that this circle over here, this radius, represent the gamma D. Reflection coefficient gamma does not change, so it's everywhere on the circle we have the same magnitude. So at this point, this B point would give you the distance ZD, so that if you look carefully here, that value would be, let's say we have 0.6 for the real value, and for the imaginary value, if I look at over here, we have 0.7, 0.5, 0.5 or 0.6. 0.6, it looked like 0.5 something. Let's see what's the value over here. So at this point, as a 0.6, 0.66. So that's the value at this point right here. All right. So that's the normalized value. To find the actual value, you have to multiply that by your actual value. So your Z0. So your ZD actual value would be normalized value ZD times 50. And if you do that, you've got 30 negative J 33 ohm. All right, that's your input value at this. That's the impedance at this point right here. All right, so that's how you use your Smith chart. Then we're going to do more problem in the class. We have more problem here. We're going to do more problem in the class. And also for the Smith chart, if you have an impedance over here, if you go on the other side of the Smith chart, it's called admittance. The admittance means is inverse of impedance. So your GYL would be 1 over GL. So that's the, if you go on the other side of the Smith chart, you get the admittance. It's very important for us to understand admittance, because admittance, we're going to use them for load matching. All right, I'm going to go through this problem in the class, and also going to go through other problem in the class to understand the Smith chart. Then we're going to go to lecture 9.